Welcome. So some of you asked for help with the practice problem because you couldn't do it on your own, or you have like some questions. So what I will do, I will also some of you asked for tutorial videos. So what I will do, I will start recording tutorial videos for the practice problem. Okay. And in this tutorial video, I'll be going like really very slow. Like in the other video, could be I just go at like not fast and not slow, at like an okay pack. So I don't bore the student who already knows these detail, and I don't go so fast for the student who don't know this. But in this tutorial, you are not required to watch these tutorials. So these tutorials are optional. You only watch them if you need to watch them. No exit tickets are required. So I will, in these tutorials, I will basically like go very, very slow and step by step, so that and very basic, so that student who need additional help can find help. And if this tutorial is still insufficient, what you can do, you can uh, come to my office during office hours, or you can email me to schedule office hours. Yeah. So let's just get started. So I get one of you asking me about this question. They were like struggling in how like the dimension of this like small k is equal to L square. So let's just do it, yeah. So how can we start approaching something like this? So start approaching something like this. Let's just say like small k, which is like permeability. That would be equal to big K, hydraulic conductivity, time mu, viscosity, over gamma Swiss specific weight. Yeah, that is like how that is. Now, let's say I don't know like the dimension of this guy, like the hydraulic conductivity. Like I'm giving you here an equation for this guy, so I can use this equation, which has things that I know the dimension of, to like find the dimension of this guy. So I'm giving you an equation here, like Q is equal to K A delta H over delta X. Yeah. Q, discharge. So I know the dimension of this guy. So what is the dimension of discharge? Remember, like this is volumetric flow rate. So that would be like volume over time. Volume rate, yeah. Volume over time. So volume, that would be like L cube over time. Because remember, length is L, area is L squared, and volume, that would be L cube. Yeah. Ka, I don't know the dimension of this guy. Area, that is like length square. Delta H, that's a hydraulic head. So I know that this is hydraulic head. This is energy per unit weight. So that will have the dimension of length. And delta X, that's like a length that will have a dimension of length. So basically that's dimensionless. So in order to get like what we have on the left hand side, what the dimension of this guy need to be. So first of all, we need to have a T here because we have a T here. So we need another T here. And then like this guy will go with this guy. So we need another L here. So basically K will have a dimension of L over T. And L, because A has a dimension of L square, and the hydraulic head gradient is like a dimensionless. Yeah. And this guy has this dimension. So now I know that K, the dimension of K is L T minus 1. Because I can like from algebra, like we know from algebra, like L over T, that is equal to L T minus 1. We know this like from algebra. So basically like you bring this up, and then this, instead of being to the power of 1, that would become to the power of minus 1. Yeah, so we know this. So I can express K with this dimension. So now I have like my first guy here, which is L T minus 1 for this case, for the hydraulic conductivity. Now, what is this guy? Viscosity, dynamic viscosity. So I know like if you can check it out like in a table. So let's see here, like let's check it out in a table. Like if you click here, for example, I put like for you here like a table and say like dynamic viscosity, it has like this dimension ml minus 1 t minus 1, yeah? Or I can drive this dimension by myself. Let's drive it, yeah? So viscosity, that is like shear stress over velocity over distance, yeah? So this basically is shear stress over velocity over distance, yeah? dv over dy, yeah? So let's, we can do it? Yeah, we can do it. So let's write it down. So like viscosity, that is like shear stress. I will just write like v over y, which is like any distance. This is velocity over distance. So can we, let me come here. So can we express like this guy, like here, this guy, shear stress, that's like force over area. Yeah, you agree? And this is velocity over distance. Yeah. So that is equal to, so from algebra, we also know that this is equal to Fa. This is equal to y over v. Like, do you agree? Like you bring this guy here and like you bring this guy here. So this guy is equal to this guy. We know this from algebra. Yeah, you agree? Can we even simplify this even more? Yeah, we can simplify this more because we know like force, that's like mass time acceleration time y like a distance over area time like a velocity. Yeah. So we know we can write the dimension of this guy. Yeah. So the dimension of this guy, what would be the dimension of this guy? So mass, that is m. Acceleration, do you remember acceleration? So acceleration, that is like velocity over time. Yeah. And we know like the dimension of velocity, that is like L over T divided by T, yeah? And from algebra, remember like you can bring this guy here, so that would be L over T squared. And also from algebra, that could be like L T to something like this. So that's like this for acceleration. So here I could just substitute this L length time minus 2. That would be for acceleration. And y, that's the distance, so that is L, yeah? Divided by area, that is like L square, yeah? And velocity, that is L t minus 1, okay? Let me delete this guy here. So can we simplify what we have here? Yeah, we can simplify. So like this guy can go away with one of these guys. We only have here. This guy can go away with this guy, yeah? This guy can go away with one of these guys, so you only have one of them. So that will leave us with m, l. I can bring this guy up, so when I bring this guy up, it will be minus 1, and that would be t minus 1. Isn't this just what we got from that table? Like, remember that table I showed you? It was ml t minus 1. So that is our viscosity. So our viscosity, it has the unit, it has the dimensions of m over length over time. M L minus 1 t minus 1. That is the dimension of viscosity. So let's see where we are here. So let me just delete this guy. So here we remember like k, we know k, like k here. We know this guy, that is already, we've seen this before, L t minus 1. And we know like mu, that is m mass L minus 1 t minus 1. And then what is this guy? So this guy here, like you can read here, it is like specific weight per unit volume. So weight per unit volume. So let's do it, yeah? So this guy here, that is weight, like force, yeah, or like you can write it like weight per unit volume. And what is weight? Like weight is like this is force, yeah, mg over v, volume here, it's not velocity, yeah. So what would be like the unit of this guy? So m, that is like mass, g, that's like acceleration, so that will have like L t to the power of minus 2, and v, that would be like volume, that is like L cube. So can this guy like go with one of these guys? So I can remove this. This would be like L to the power 2. So here it will be m. I bring this guy up, L minus 2 and t minus 2. Yeah. So now can I write like this guy here? M L minus 2 and t to the minus 2. Yeah. So I have like oops. So now here is my small k, which is permeability. Basically, permeability tells you how the pore space are well connected together. Yeah. So if you have high permeability, you have high like flow could occur. If no permeability, flow will not occur. Yeah. High permeability, you can get like high flow rate. Low permeability, you get like less flow rate. Yeah. So what do we can we simplify this guy? Remember, like the final solution is like L squared. So can we like simplify this guy? Yeah, we can, because we can like this guy can go away with this guy. Let's even remove him, yeah, because here we can remove, yeah. Let's see what else can we do. Can this guy like here? This is like t minus 1 and t minus 1. Can this go away with this guy? So we can remove this guy and this guy and like this guy here, yeah. And then this is to the power of 2. So can like one of these guy like go with this guy. So like we can get rid of this guy and just make this guy minus 1. So what does minus 1 mean? Minus 1 means that we can bring him up, yeah? And this minus will be positive. So that would be like L times L, and that will give us like L squared, which is the solution that we have here. So we know now, so we have like here a problem. This is like the hydraulic conductivity, but the hydraulic conductivity is a function of two things. It's a function of permeability, which is the property of like the porous media, and it's a function of viscosity and specific weight. Yeah, like viscosity and specific weight, which is a function of like the fluid. Yeah, so different types of fluid will have like different viscosity and specific weight, and this different type of geological material will have different permeability. But this is not important for this course. The important part is that you know how to conduct dimensional analysis, like to find the dimension of this guy, and this is very important for problem solving, because I just showed you like this guy, you don't know anything about him, yeah, but by just like playing around with these things, you can find his dimension, and you know that this guy is an L square guy, yeah, something like this, yeah, okay. So this is this problem. The second problem, I think this is like the Bernoulli's equation. So let's do it here, like, you know, pressure. Do you know, like, do you remember, oops, do you remember pressure? Pressure, that is always like force over area, and force, that's like mass acceleration over area, and that would have like the unit of m, L, t minus 2, and here that would be like over L, yeah. So what does this mean? This means that like this guy could go away with one of these guys. We can delete this guy. We can make one of this. Then that would be m L minus 1 t minus 2. Yeah. So just write it here. So that's like m L minus 1 t minus 2. Yeah. That's the dimension of this guy. Density, you know, that's like, what's density? Density, that's like mass over volume. So mass, that is like m, and volume, mass, that is like m, and volume, that's like L minus 3, mass over volume, yeah? Velocity, we know this guy, that is like L t minus 1. Acceleration due to gravity, that's like, oops, t minus 1. Acceleration due to gravity, that's like L t minus 2. And distance, that is L, yeah? So we have like everything we have here, and then let's just substitute, yeah? So pressure, what's pressure? That is like M L minus 1 T minus 2, yeah? Over density, what is density? That is like M L minus 3, yeah? So what will happen here? Like this guy will go away with this guy. This guy will go away with this guy, and then this will be minus minus 2, yeah? So basically, can I just like flip it? Like bring this guy up and bring this guy down, yeah? So that will give me like L square over T square. So that would be my first term here, yeah? That's like energy due to like pressure gradient, yeah? That will give L over. Can we do this guy, like V square? So V square, that is what? Like, so V velocity is L over T. And then like we square this guy, so that's like square. So that would be like L square over T square. So that is like L. So that is L over T square, yeah? Which is, so that's for the velocity, yeah? Which is what we have here. 1 over 2, this is like constant, it's dimensionless, yeah? So 1 over 2, this is like 1 over 2, 1 over E, 1 over, I don't know, I don't want to write infinity here, but 1 over like anything, that's like a constant, so that's dimensionless, yeah? That's just like constant, that's dimensionless. Okay, so that's V, yeah? And then let's do the last one. So this is like energy, like kinetic energy, yeah? And then let's do this one, that would be like due to potential energy. So potential energy, that would be like Gz. So G, what do we have for G? That's like, oops, that is like L over T minus 2. And Z, that is L. So that will give me L square over T minus 2. Yeah. So, let's see here. Okay. So here, G, that is like L over T square, sorry. And then that is like L. So that will give me like L square over T square. Yeah. So here, L square over T square, L square over T square, L square over T square. So, and so this constant will have the unit of L square over T square. So that would be the unit of this constant. This term here, let me just like delete this guy. Let me delete this guy. This term here will have the unit L square over T square. Yeah. This term here will have same L square over T square. Sorry. This guy here will have L square over T square. So what does this tell us? So this basically tells us that this thing, this equation is dimensionally homogeneous. Why? Because they all have the same dimension, L square over T square. The energy due to like pressure gradient, kinetic, and potential. Yeah. So, and this constant, whatever this constant is. Yeah. Okay. So basically, that is the tutorial for week 1, and see you in the tutorial for week 2.